Hello everyone. In this lecture I will be discussing about vibrational rotational spectra. In a previous lecture we have discussed about the pure rotational spectra. The vibrational rotational molecular spectra arise from the transition between vibrational energy states associated with the same electronic state of the molecule and are obtained in a near infrared region of electromagnetic radiation. In a similar case of a pure rotational spectra, the vibrational rotational spectra are obtained only for the molecules, those having the permanent dipole moment. It means that we could only observe such vibrational rotational spectra for a heterogeneous heteronuclear diatomic molecules. So in this case, once we have a molecule, diatomic molecule, this respective atom is vibrating with respect to its equilibrium position. Then, due to these oscillations, there is change in their energy levels. So, the dipole moment change periodically with the frequency of vibration. Suppose nu oscillating is a frequency of a atom or the molecule which are vibrating at their respective places. So then once you have this permanent dipole moment, due to these vibrations, there is a oscillating dipole moment. Such a molecule on a basis of a classical electrodynamics leads to a emission of a radiation for a frequency V oscillation. And at in addition, if it interacts with the electromagnetic radiation, it absorbs the radiation having the same frequency, this new oscillating, because that is a resonance frequency. So the homonuclear diatomic molecules like H2, N2O2, which necessarily have zero dipole moment for all internuclear distances, fail to interact with the radiation and so give no vibration spectrum. The presence of any oscillating dipole moment is a must for an electron with the oscillating electric field of radiation. Such molecules, however, give Raman spectra. So these homonuclear diatomic molecules may provide you a Raman spectra, but not a pure and a vibrational rotational spectra. In practice, vibrational rotational spectra are observed in absorption. Generally, once we are interacting electromagnetic radiation through this molecule, then it is these molecules are absorbing certain band, then they are providing the absorption band. From there only we could say that these are the vibrational spectra. The spectrum of molecule like HCl consists of intense bands known as a fundamental band, accompanied by a number of weak bands, that is overtones, at wave number approximately double, triple of the fundamental. So in this spectra, if you look at, this is the highest band, that is the fundamental band. Then you have this, in this x-axis you have a wave number, that is a frequency. Then you have the overtones, but their intensity is comparatively very, very less. We will end of this talk, we'll be discussing about the same. The The fundamental absorption band is found to consist of the two close maxima. For in this case, we have two fundamental close which are isotope effect. For this is the wave number, this is the HCl. So we have a very close bands. So this is the HCl37 because it is an isotope, it having the heavier nucleus than it having the lower energy, and the HCl35 having the higher energy. This wave number is a higher wave number side. The overtone bands successively appear with a rapidly decreasing intensity when the thickness of the layer of the absorbing diatomic gases increase. So once we have these are the absorption bands. Once we have a very high resolution spectrometer, within these bands we having the thin lines, equidistant lines, and these lines are called the fine structure of infrared bands. So this is my band. Suppose within this band we have a small lines. So these are called the fine structure of infrared bands. And in the series of lines which are not equidistant, a line is missing in the center of the band. The missing line is known as the null line or the zero gap. Further, the lines show a rather poor tendency of a convergence towards the high wave number side, and the band is said to be degraded towards the low wave number side, that is towards the red side. Means this red side means you are moving towards the lower energy side. If we are saying that blue side, then it's a high energy side. Now once we are saying that these atoms are vibrating with their respective places, so we can presume, we can assume that in a robust approach that this particle, this molecule behaving like a harmonic oscillator. Means kind of the two atoms are attached with two masses are attached with a spring. So with that analogy, we could say that it behaves like a harmonic oscillator. So the molecule as a harmonic oscillator. The near-infrared spectra are attributed to the vibration of the nuclei in a diatomic molecule along the internuclear axis. The simplest possible assumption about the form of vibrations is to treat the molecule as a harmonic oscillator. If you remember, in the quantum mechanics itself, in a classical mechanics itself, the potential of a harmonic oscillator is parabolic. So the potential for such molecule we can define this Vr is equal to 1 upon 2 kr minus Re square, or Vr is equal to 1 upon 2 kx square, where k is a force constant, x is a displacement of oscillator from the equilibrium position, and Re is the equilibrium intermolecular distance. Re is intermolecular equilibrium distance. So if I will write a Schrodinger equation for a harmonic oscillator, time independent Schrodinger equation, then this is d squared psi by dx squared. This is in a one-dimensional case. We remember that this one-dimensional case because this motion is taking place along the axis of their bond axis. Then d squared psi by dx square is plus 8 pi square mu divided by h square, and e minus half of kx square psi is equal to 0. Now this mu is my reduced mass of the oscillator diatomic molecule, because we have already considered this a single body problem. Even in a rotational spectra we have made such kind of the equation. Now we are defining two parameters over here now. Now alpha is equal to 8 pi square mu e divided by h square, and beta is equal to under root 4 pi square mu k divided by h square. So once I will put these equations a and b in equation number 2, what I will get is d squared psi by dx square plus this is the alpha, that is the alpha, minus this is beta square x square, this is whole quantity becoming my beta square now, and psi is equal to 0. Now again we are introducing an independent variable, that is the dimensionless. So xi is equal to under root beta of x, the change of the variable. So once the change of the variables, this is crucial. And now once you will be looking this expression from your textbook from the Rajkumar, then it is written that this xi is equal to root beta x, and then simply so that it is d square divided by dx square is equal to beta of d square by d xi square. So here is simplify it is already. So xi is equal to root beta of x. Then this d psi, suppose any function we have, then d psi by d xi is equal to what I could write, d psi by d of root beta x, because I have kept that xi is equal to root beta of x. From here, the d psi by d xi is equal to root 1 upon beta, root beta d psi by dx. Now again we have to take the second derivative, because I have this, here is a second derivative. Then d square xi by d xi square, here must be d square psi by d xi square is equal to 1 upon, again d psi of 1 upon root beta of d psi by dx. Then simply this putting this on root beta outside, then again d square by d square psi by d psi of dx, again putting the value of chi over here, then you have d square psi by d xi square is equal to 1 upon root beta, and again in place of this xi you have this root beta x, then finally you have this root beta 1 upon beta, then you have this dx of d psi by dx, then finally d square psi by d xi square is equal to 1 upon beta d square psi by dx square. Then now the change of the variable, now we have found that d square divided by d xi square is equal to 1 upon beta of d square by dx square, or d square by dx square is equal to beta of d square by d xi square. Now this relation. Now putting this relation, this d, in equation number 3, now putting in this relation simply, in place of d square by dx square, then simply change of variable. Now you have beta of d square by psi by d xi square, plus you have alpha minus beta square, then this is xi square divided by beta. This xi square divided by, in place of this beta x, this is the xi square, simply this is xi square divided by beta square, that is beta or psi is equal to 0. Then simply, then dividing with the help of the beta, this is alpha divided by beta square and beta, and the 1 beta is coming from here, then is cancel out, then psi is equal to 0, equation number 4. Now this is a simple second order differential equation. Then this is a most suitable solutions are the exponential or the oscillatory function. So the solution of this differential equation, we assume that this is the oscillatory function psi of xi is equal to c of u and xi exponential xi square divided by 2. So this u of xi. Now we have to put, we have to estimate the d square xi divided by d xi square to put in this relation. Then simply what I will do, this psi I have in this form, the solution. Now we have to satisfy this equation number 4. In that case, what I will do, just taking the first derivative, d psi by d xi, just taking the derivative of it. So you have a two function. The c is your normalization coefficient, then u and these are the two functions of this xi. Then you by one you are differentiating simply this c of du by dxi exponential of xi square divided by 2 plus then the c of u, then again differentiating this function, then finally you have this c of du by dxi of exponential xi square divided by 2 plus cu exponential of xi square divided by 2 minus 2 xi by 2, because taking the differentiation of this one, right? Now again, now finally you have the d psi by d xi is equal to c du by dxi exponential xi square divided by 2 minus c xi u exponential xi square divided by 2. Again, because I have to take the second derivative, again once you will take the second derivative of it, then again you have two functions over here, u and exponential of this one. Then you have a c d square by u by dxi square exponential this plus again c du by dxi and exponential xi square divided by 2, then minus 2 xi divided by 2. Now here you have three functions, xi u e exponential of xi square divided by 2. Then you have this one by one, we have to take the derivative of it. Then c dxi by dxi, then these two functions plus xi, then du by dxi, then plus the derivative of this one. Then once you will be simplifying it, then finally you will be achieving that this c of du square by dxi and this term coming in a minus. Now dxi by dxi is 1, then we have simply cu of exponential of this one minus you have this term c of xi du by dxi exponential this, and this term is plus of because minus is over here, then again 1 minus coming from here, then you have a positive one. Now once you are putting the value of d square by d xi square in this relation equation number 4, then simply putting this relation over here, then you have alpha divided by beta, then you have a psi. In place of the psi you have this c or u xi exponential xi square by 2, then alpha divided by beta c u and exponential xi by 2, and this minus xi square, then this is xi square, then c u, in place of xi you have c of u of exponential this one. So now the exponential of xi square divided by 2 cancelling out from everywhere. Then this term c is also cancelling out from everywhere. Now simply you have a d, this term is remaining, the d square by u by d xi, minus one term is remaining from here, xi du by d xi, minus one term appearing from xi du by d xi from here. Then this alpha divided by beta, this is the u minus this one. These two terms are cancelling out. This term and this term will cancel out. Okay. Now you have a differential equation now, d square by d xi square minus 2 xi du by d xi alpha divided by beta minus 1 of u is equal to 0. Now again this quantity will be replacing with the help of 2 nu, and it becomes a Hermite differential equation if you remember. Also replacing this u of xi, that is a u, with the help of h nu of xi. Then I have a differential equation, this d square h nu of xi divided by d xi square minus 2 xi d h nu xi divided by d xi plus of 2 of nu h nu xi equal to 0. Now I have a Hermite differential equation, which shows that the solution of equation number 4 is obtaining by replacing u xi by the Hermite polynomial s nu of xi in equation number 5. Then it becomes, we have the solution. So these are the acceptable solution as we know from the Hermite polynomial, only for if nu is equal to 0, 1, 2, 3 and so on. The restriction on nu gives a corresponding restriction of E. So because nu is related to my energy. Now this alpha divided by beta minus 1 is equal to what? How we replace these 2 of nu? From equation number 4, A and B, from equation number A and B. So equation number A and B, we have these two relations. Now I have got this relation in the alpha and the beta. From here alpha divided by beta plus 1 is equal to 2b. Alpha divided by beta is equal to 2b plus of 1 or nu. Then this 8 pi square, this is equal to this. From here finally I will get what I will be getting, that this E is equal to h upon 2 pi under root k upon nu mu, this nu plus of half equation number. Now if you look at, if I am assuming that this is a kind of the harmonic oscillator attached to the spring, then this 1 upon root 2 pi under 2 pi k upon mu, that is the classical frequency of the oscillator, that is the fundamental frequency, what you could say. So now this energy is becoming my h nu oscillating nu plus of half, where this nu is equal to 0, 1, 2, and this is a quantum number. This is a quantum number, however this is my frequency. Be careful. This is the rotational quantum number. This gives the allowed energy for the harmonic oscillator. A special feature of the quantum mechanical oscillator is the existence of the 0 point energy, because if I am putting this value of the 0, this energy is not 0. That is the 0 point energy. Now let's investigate the expected spectrum of such an oscillator, the vibrational term, that is energies in the wave number. If I have to calculate the energy in the wave number, simply I have to divide with the help of the hc. So this, now I'm representing this wave number, this g of nu is equal to E upon hc. Now just dividing this quantity, the h cancel out, this h oscillating divided by c, and this quantity we know that is a classical frequency that is in a wave number and is known as the vibrational constant, denoted by this omega. So then we have g of nu is equal to omega nu plus of half centimeter inverse. That is the energy. So again, now once we'll be putting that the nu is equal to 0, 1, 2, 3 and so on, then we have these different 0 point energy, first excited, second excited and third excited state. Exactly in the quantum mechanics, what we got is 1 upon 2 of h cross omega, 3 by 2 h cross omega. Now here we are representing in the wave numbers. So once we have a series of equispace discrete vibrational levels, the common separation being is just omega centimeter inverse. Then we have a 0 point. Now once we will be plotting these frequencies, this is my potential. Then this this energy is not at zero. You have some finite energy. Then when a transition take place between an upper level nu prime to a lower level nu double prime, the wave number of the emitted or the observed radiation is defined. This nu is equal to g nu prime minus this one. And simply that is omega nu prime plus half of this one. So harmonically oscillating molecule of dipole moment m, that the matrix element is formed to be the non-vanishing only when dm by dx is equal to 0 and delta nu is equal to plus minus of 1. So that is the condition. Once we will be taking that we haven't discussed about the time dependent perturbation theory. Once you will be dealing these problems with the time dependent perturbation theory, because you have an oscillating field with respect to time, it is oscillating, it interacts with the your molecule. Once you will be once you will be computing that the dipole moment of this, so I'll be getting some matrix element. That matrix element has to be non-zero for a permanent molecule having the permanent dipole moment. So this is the condition that the permanent dipole moment should not be zero. And then these are the allowed selection rules for the vibrational quantum numbers. So now these transitions are taking place only for the allowed levels of this delta nu is equal to plus minus 1, which keeps that the levels are considerably larger than the spacing between the rotational levels of the molecule, in fact larger than the k of t at room temperature. The reason is that as we have these vibrational levels are in the same electron states, and within these vibrational levels you have a rotational space, and in generally these vibrational states are falling in infrared region. However, my rotational spectra are falling in a far infrared or the microwave. So the most of the molecules in a sample exists in a nu is equal to 0. That is the ground state. That is the 0 point energies. Except that the heavier molecule which have the smaller vibrational spacing, because due to that heavier is nucleus, thus the main vibrational transition is absorption is that is nu is equal to 0. That is the v of v is equal to 0. Means something is they are observing it much, they are lifting from the to the higher energy levels. So the absorbed wave number corresponding to this transition, once we will be calculating, estimating this nu prime is equal to 0, nu prime is equal to 1, then you have simply this nu is equal to omega centimeter inverse. That is the wave number. So thus the vibrational spectrum is expected to consist of a single band at omega centimeter inverse. The absorption of a very intense band in this infrared spectrum thus leads to the conclusion that the vibrational spectrum, the nuclei carrying out a harmonic vibrations along the internuclear axis. However, the weak occurrence of an overturned band with nearly 2 or these terms are frequently still to be explained, and they connected to the deviation from the oscillations being harmonic. So what this robust approach we have applied over here, that is a diatomic molecule. This is behaving a kind of the harmonic oscillator. In practical, the sum of the overtones have been observed as the selection rule delta nu is equal to plus minus 1, and this is slightly deviating from its harmonic nature. So if there is a transition taking place of the rules delta nu is equal to 2, suppose there is a transition taking from this nu double prime is equal to 0 to nu is equal to 2, nu single prime is equal to 2, means there is a huge gap. So now you have over 2 and 3 times higher wave numbers you are achieving. So these are called the overtone. So any resonant frequency So we have a resonant frequency. So any resonant frequency above the fundamental frequency is referred as a overtone. So that will be explained once we will be discussing about the molecule as an anharmonic oscillator. For today, we have discussed about the vibrational rotational spectra. Thank you.